Okay, I think others are still joining here, but we will get started. Good to see people for today. We are continuing our path through a set of important but not deeply, not tightly ordered concepts and topics here. Uh, Today, we're going to be discussing one that has great significance for model behavior, for understanding of how model behavior relates to empirical behavior observed, and frankly, for understanding behavior we do see from the world, in as much as our agent-based models form these sort of mimics, simplified mimics of the world. A lot of what we see expressed in their behavior helps us learn about similar behavior in the world. And one of the things we learn is just how much emergent structure there is in systems in the world, in systems that maybe at a nominal, which are composed of many interacting pieces, but where it's necessary to reason about that behavior, to recognize the profound coupling across the system gives rise to actually much lower dimensional behavior that can be where at any one time we can describe the system often in a much more parsimonious way than we might think. So what I'm going to speak about today, and it may continue till next time, really provides an avenue towards and an on-ramp to many issues in what I termed many years back and continue to refer to as systems data science. This true synergy between a system science perspective and a data science perspective that recognizes the need for each to learn from and enrich itself by drawing on techniques, insights from the other. And we're going to begin here with some basic material, but likely develop it in a way, perhaps as soon as next session, that points the way to its relevance in the data science context. So to that end, I'm going to share my slides, and I do apologize because of an urgent matter that came up. I wasn't able to post these slides before the session. I will seek to do so immediately after. And the title there may be mystifying or perplexing or off-putting to some, but I hope you'll recognize that terms such as intrinsic dimensionality or state space reconstruction for the very important, valuable, and actually far-reaching implications that they have. So I had noted in my opening remarks here the fact that this is material that relates to, it speaks about the interface between and the relationship between modeling on the one hand and our understanding of patterns in the world. You know, when we do modeling of this sort, when we build agent-based models, hybrid models, you know, often we're seeking to put forward a theory that helps us reason about, better explain, explicate, better understand systems in the world helps us better understand the empirical patterns that we see from the world and ask critically, and very different from the vast majority of machine learning techniques, for example, how those patterns would differ in the event of counterfactuals. We spoke about this some last time with scenarios. But if we ask about, for example, the impacts of interventions or the impacts of policies more generally, or we think about the impacts of exposure to exogenous events not under our control, an economic downturn, disruption in supply chains, adverse set of climate developments, reasoning about how the system would respond to this. So here, without making it sound too fanciful, we have an underlying system evolving, and it's a nonlinear system. These many, if anything, these many models we've examined with susceptibles and infective should have conveyed the fact that it takes two to tango, that one can't simulate just the infectives and then separately just the susceptibles and add the results up and expect to get something comparable to the results of simulating both together. It doesn't work that way, right? You just like you can't divide a person in half and have each part just operate independently and somehow say, well, the whole person is just the sum of what those parts would be in isolation. It doesn't work that way any more than a traffic jam. If you were to separate each car and put them separately and ask how they behave, the behavior of a traffic jam is different, profoundly different than that. It's about not the pieces, but the interactions, right? And so it's nonlinear in general. We have these interactions of effects that make the whole greater than the sum of the parts or different than the sum of the parts. And it's coupled, and this is going to be a key part in this discussion. What goes on in one piece ends up affecting another. It's pervasive, it's promiscuous. Things that happen in one part of the system ripple through to what happens to you. If you're in a traffic jam, the braking behavior of someone 100 meters up may affect what you see a few seconds later, right? The fact that someone's infected across the country with measles can lead to you to get exposed, and if you're unvaccinated, to get sick, right? It's coupled. These things affect each other in big ways, and much of agent-based modeling is focused on understanding this coupling between agents and environment. But, if we think about it in terms of data science and empirical observation, this system gives rise to data. It's not data that comes from heaven, is it? It's in the form of measurements, and those measurements are often delayed. They're sometimes non-continuous. We don't have the luxury of collecting them as frequently as we'd like. Often they are incomplete, they're noisy. Sometimes they omit certain parties, sometimes those most vulnerable. And they're sometimes erroneously attributed. We sometimes measure one thing and we think we're picking up something else. Now, these measurements, though, induce patterns, associations from the world. And much of statistical science, much of biostatistics deals with these patterns. And, good statisticians who do the biostatistics will speak about the data generating process, sometimes a little bit bluntly, but really referring to this whole area beneath this, with the eye and below. And of course, when we do dynamic modeling, we're dealing essentially with that data generating process, the underlying dynamics and reasoning about the observations, partial though they are, scattered though they are, incomplete though they are, within that system. Now, time and time again in this class, and more broadly when presenting results of a simulation model, we've tended to focus on behavior over time of certain variables and displaying that behavior in behavior over time graphs, where we have time on one axis and vertically we might have the value of a given variable. Maybe we put multiple, state variables on it, S, I, and R, right? The number of susceptibles, the number of infectives, the number of recoveries. And over time, those each arc, etch out curves, right? Now, we're going to be speaking today about state space, the underlying space by which this system evolves. And this provides a different lens. It's an alternative way of depicting, but also of giving insight into model evolution. Many of you will have encountered this before. Each element of state space, maybe if we're dealing with a compartmental model, each of the values of each of these compartments, the number of susceptible, number of infective, number of temporarily immune people, are plotted in a plot. So at any one time, the system is in a specific point in this space, a space whose dimensions are each of these in turn, each of the elements of state of the system. And at any one time, it has a certain value of S, that's the number of susceptibles at that time, a certain value of I, that's the number of infectives at that time, and a value of temporarily immune people, right? So we have these coordinates, and we can plot out the evolution of a system within those coordinates. So when we visualize state space with a compartmental model, really where the state is very contained. Here we have three nominal state variables. We have a three-dimensional state space, one for each of the state variables. And I've shown a given run of the model is arced out by a trajectory, right? It starts at a particular point at the initial time, and it goes on from there. So you could imagine a little point running along here and evolving and going around and maybe it's reaching an equilibrium where that little ball is going to stay and fixed down here. So at any one time, as I said, it's going to have a certain value of S, a certain value of I, and a certain value of T that dictates where it is along this path, but it will be passing along. And time is marked by passing along this thing. It's somewhat implicit here. Now, for a nonlinear model behavior often differs dramatically across the state space. We'll see some examples of this. But something that it's important to understand is that this state space nominally may be of a certain dimension. Nominally in the sense that naively at first glance, we may think here, well, there's three state variables, so there's three axes here that plot out the value of this, this, and this in three-dimensional space. But in fact, the characteristics of the state space reflect the structure of the model and the interactions in the model and the coupling of the model and the behavior of the model, in short. And in this case, and this particularly very simple case, it's something that nominally looks like it is three numbers that are needed to characterize its state at any one time, S, I, and Ti. In fact, we're overstating how much information we need because if we have a fixed total population, which I'm assuming here, a fixed total population, anyone who leaves Ti goes back to S. There's a conservation of people here, right? People never leave the system. The total population is fixed. And therefore, if we just have two numbers, S and I, we can figure out what the third one is. It's just this constant, total population, minus quantity S plus I, right? So in fact, the state space, which at first glance looks three-dimensional, is in fact, in this case, two-dimensional. It exhibits just 2 degrees of freedom here. And if we look at it from the right angle here, from the correct angle, from the appropriate angle, we will see that it has just 2 dimensions, right? By contrast, a system where the total population of somewhat similar structure, but where the total population is not fixed, for example, maybe people come into the model with births and die from the model or leave the model. Here we will not in general have a 2-dimensional space. It may occupy a genuinely 3-dimensional space. Now, I'm not going to dwell on the features of this. I could hold forth for quite a few lectures on this. There's fascinating, geometry and dynamics associated with this. There's often equilibria like this one here that exist, and they form different sorts of equilibria, situations where the system is at rest. You can get these sort of attractors that pull things in. You could get limit cycles where the system cycles around a certain point, like with predators and prey. And you can actually get that in some health models, including some I've provided to you in the model library. And one can catalog and characterize the types of equilibria, but that would need to take into account the dimensionality of the ambient space, the space around it. There's some wonderful mathematics associated with it, some mathematics associated with the stability of these equilibrium, the Poincaré-Bendixson theorem relating to possible behaviors of it, having ranges of stability over which a given equilibrium is resistant to change, where you're just drawn back to the equilibrium as long as you stay in a certain area of it. And in general, there can be basins of attraction where, those in one area of the space are drawn to one equilibrium and those in others to different areas. So, for example, we may start out here and we're drawn up and we end up in this equilibrium. If we start with 200 healthcare workers and a certain number of infectives initially, we end up here. But with just a little bit smaller number of initial infectives and the same number of healthcare workers, we end up in a very different area of the state space. And we end up going and being captured by a different region of the state space. I'm sorry, it's this one. If we start here, 1,400 initial infectives, we'll go down, the infection will die out, the health system will be able to control it. But this one, slightly more, it will go into a radically different regime, a radically different mode of behavior, where it will reach a different equilibrium where the infection will stay endemic, where it will remain in the population. These are called different basins of attraction. This basin, it's kind of like you have a drop of water, it will flow down to Hudson Bay. And this one, if you have the drop of water just over the crest of the mountain, it will flow down into the Fraser River and out into the Pacific Ocean and the Strait of Juan de Fuca, whatever, most of that. Okay. Now, some of you will have noted, and perhaps with a certain degree of impatience, that what I've been talking about here thus far is really dwelt upon aggregate models, compartmental models. And I've done so in part because they're easier to draw the state space and to visualize certain things. But what I've said applies, but it applies with some extra fascinating twists to ABM. And this is going to get into some of these issues with the intersection of system science to data science. So look, agent-based models are in general very high dimensional systems. Nominally, we have an extraordinarily abundance, a astonishing number of different possible states of the system. So look, if you have agents and they each can be in just two possible states, let's say employed, unemployed, right? The number of possible states of the system of n agents will be rising as 2 to the n. With just one person, we have 2 possibilities, right? With 2 people, we have 4 possibilities. Person A could be in either of their states. Person B could be in either of their states. With 3 people, we have 2 times 2 times 3, 2 or 8 possibilities, right? Person A can be in any of their states, either of the 2, B in either of their 2, C in either of the 2. I get students in my undergrad class who get confused and think there's a factorial here. There ain't no factorial here. It goes up exponentially because person C doesn't constrain what person B can be and what doesn't constrain what person A can be in, etc. And in general, if they can be, a given agent can be in one of S different states, the number of theoretically possible states in the model is S to the n, right? It bears sober reflection that if we have one state chart where they can be in one of 2 states and another where they can be one of 3 states, each agent can be in, although we can express it concisely with these state charts, just showing 5 states, their number of state combinations for that one agent is 2 times 3. And then if we consider extra agents, that's the n different agents, we get multiplicative. So there's a cursive dimensionality here. There's a dimension, an explosion, geometrical explosion, right? Some people might call it, I'd forgive you if you call it exponential. Although commonly we reserve that for continuous functions. So state space diagrams here don't depict the complete state of the system. It's not like we could show the number of infectives here, the number of susceptibles here, the number of infectives here, and have a complete description of the state of the system. But we will use, to great effect, with great power and insight, state space diagrams that summarize agent-based state at any one time, where we may, for example, project down the full state space, of agent characteristics to a number, to a count, say, of those infected or those susceptible. And here we're abstracting over whether it's, if we have Mary, Sue, and Sam, whether it's Mary who's infected, Sue and Sam are still susceptible, or whether it's Sam is infected and Mary and John are susceptible, or whether it's John is infected and Mary and Sam are susceptible. We abstract over that and we just say 1, right? 1. Now, it's blunt, but it does afford us a chance to use state space diagrams with an asterisk, right? It's not the full state space. But even this can give us great insight, and we end up recognizing some features here. So I'm gonna be speaking about that. So here are the ABM state space trajectories are typically stochastic, and there's typically only a thin, what I'll call manifold of it that's explored. And I'm gonna come back to this point. So some of you may wish, and I'm not gonna do it right now, but just because of limited time. But I would note that if you open up any logic and you go to the example models, there's a thing called the predator-prey agent-based model. A predator-prey agent-based, I think it's called. And it depicts in a space. And I need to think that there may be a variety that I've augmented that I need to post, but so we have a space, and we have prey, which are shown in green, and we have predators, which are shown in red. Okay. And the predators move around, and they're chasing the prey, and the prey move around. And when a predator comes into contact with the prey, it does not end well for the prey, and they eat the prey, and they get some energy, which allows them to be sustained. If they go for a certain amount of time and they can't catch a prey, they will die. The predators will die, and there's births and deaths on a regular basis of each population. Now, what's notable, and I'll upload the model, which find this, if we plot out the numbers from this model, so here's the hare population over time, and here's the lynx population. I note this with a certain degree of pride for the fact that numbers like this were noted first. I've records of the Hudson Bay Company in the Northwest Territories, as it was called in that time, which included Saskatchewan and Manitoba, and where there was trapping going on of hares and lynx, and the voyageurs and others engaged in trapping, the trappers on their trap line, noted that when hares were very rare, there tended to be recently a lot of lynx. And when hares were very, very numerous, the lynx population would often soon rise, and the hare population will be due for a decline in some years later. And we can kind of see that here. These are not solitudes, right? The fact that the hare population is high here is a reflection that the lynx population has been high, but that high hare population leads to a rise in the lynx population subsequently, because the lynx are eating those hares. And that leads, just as the night follows the day, to the hare population to decline, the sudden decline in the lynx population, but a rebound after the hare population rises again. So there's these couple dynamics. But these dynamics are a reflection in the world, and indeed in this agent-based model, of a complex set of high-dimensional interactions, right? Many of these lynx and hares hopping around in the snowy wilds of northern Manitoba. And here I show the state space plot, or a state-based summary plot, right, of hares on the x-axis and lynx on the y-axis. And what you note, there should be pause for thought. Not P-A-W-S as in hares, but P-A-U-S-E. So here we have actually two basins of attraction. I actually changed the parameters. It was in this basin of attraction before. It was circling around this point, and then it circled around this point. But what's notable is that this system has structure to it, right? Like the state space, it's not occupying willy-nilly in a sort of just random way, the entirety of the state space. There's structure here. There's circling around a certain area that whispers of the structure underlying these time series. At first glance, to the casual observer, to the callow youth who's engaged in too much brain rot, this may look like random sequences with no particular structure. There is hidden structure behind them, right? And that hidden structure is spoken to us by the state space plot. The state space plot is indicating a certain codependence here between these two. You'll notice that all these trajectories head in one direction here at certain areas. They're circling around much as planets to the sun, or solar systems around the galaxy. There's a logic to these time plots that is hidden in their structure and which could be ignored or it could be overlooked by someone who is a rando, and but which is spoken here and hinted here in the state space plot. The state space plot is indicating some codependence here that is deeper in it. Similarly, I've shown here for an infectious disease model where the system moves between two states associated with lower infection and higher amounts of infection. Now, again, I apologize. I'm not going to run it here, although I may in a future lecture, perhaps in our coming lab session, really explore some of these. I've tried to provide two examples you could look at. One is the hares and the fox, the lynx and the hares. Another is this crowding disparities one. Here you may recall it. We have a population which exhibits heterogeneity, profound disparities in income, and the income induces crowding here. And what one sees again is some sort of lower dimensional structure, some sort of circling around in equilibrium if we look at the summary state space. Now, this may look unremarkable. This may look like, well, okay, so it's kind of a fuzzy blob. Yeah, what of it? But it bears noting that nominally speaking, with hundreds of people in this model here, with hundreds of these agents, these hares and perhaps many hundred also of lynx. Despite that, we have quite contained low dimensional spaces. You might think with all those different agents, you would have no rhyme or reason. This would be just a buzzing, blooming confusion of kind of cross trajectories and kind of, no rhyme or reason to it, just a fuzzy mess occupying this whole area because you've got all these agents doing different things. We're just projecting this down to just two dimensions. How could we ever expect to have any regularities in just two dimensions, summarizing this massively high dimensional system where every agent can be in different states, etc. That will be understandable. You could be forgiven for thinking about that, but you would be wrong. In fact, there is very pronounced low dimensional structure, even two stinking dimensions. You start to see the structure of this, this low dimensional regularities, that it's circling around a certain point here. And yes, it differs a little bit on who's infected, whether it's the rabbit named Mary or the hare named Sam or what have you. But the point is that it actually has very regular behavior at a certain point. It's at any one point, any one set of parameters, it's cycling around a certain attractor. It's cycling around a certain point. And with just two numbers, you can be pretty confident within a range of uncertainty that's quite bounded where it's going to go next. Again, I changed parameters here and it's going around this one. But again, if you have it here, it'll likely go, I believe it's circling this way, counterclockwise. It'll sort of proceed around here, much as the Earth circles the sun or the moon, its mother orb. So we get a similar thing here, hundreds of agents. But there's something going on that there's this coherent behavior, this kind of low dimensional behavior, this sort of deeper orderliness or regularity coming out of it. It's not just, helter-skelter with no particular patterns. We've hinted at this, haven't we, in some previous explorations. We've seen, for example, induced from a model like this, these associations, these kind of low-dimensional associations between income on the one hand and infection burden on the other. These are not, again, just all over the map. Even though this is summarizing hundreds of agents, there's clear order here. There's clear structure here emerging in the emergent patterns from this. And I argued that orderliness in the underlying model, the fact that we have these, yes, we have so many agents, but we have networks, we have regular progression among different states, we have rules for interaction of different agents, induces regularities in the behavior. Here it's for low socioeconomic status and high socioeconomic status. With respect to two particular outcomes, you see very clear kind of indicators of the behavior of different parties. This should remind you of that first graph or that first SITI model that I showed. Pivoting back to sort of the aggregate character, I argued that, well, nominally we look at this three-dimensional, what seems to be a three-dimensional space and require three numbers to summarize it. In fact, it was lower dimensional than that. In fact, there was enough structure, enough regularity there, enough conservation in that case, that the results were in fact summarizable not in three, with just three summaries of the state variables, but two. Here we're going from millions potentially or more down to two that pretty well describe a lot of the dynamics. Now, we could, plot this out further. This is hair versus lengths. This is also another aspect of regularity. Lengths on the x-axis versus lengths 1 time unit ago. And as you might expect, if I count the number of links now and count the number of links yesterday, there's going to be quite some correlation there, isn't it? Right? I mean, if there's 500 links now, okay, well, maybe there's 490 yesterday, or maybe there were 510. Maybe they're going down, but there's, the value now tells me quite a bit about the value yesterday. There's quite a bit of information if you tell me the value now for what the value was yesterday. And same thing with hairs. But, the fact that we know, for example, up here, that linkses are very high up in number, as I indicated before, and with reference to this, it's going to tell us something about what's in due, what difficult fate was due for the hairs, right? If we have tons of linkses around, it's saying something about the hairs, how the hair population will be changing. High links tend to presage a drop in the hair population. So I'm going to distinguish here, importantly and repeatedly, between nominal dimensionality, the naive dimensionality of a state space, something like this, where you say, well, this is just three state variables, versus the intrinsic dimensionality, here closer to two. It's only exercising two dimensions. And here we have massive nominal dimensionality, but the intrinsic dimensionality, I'm arguing, is much smaller. The exercise dimensionality. It's as if, folks, we have embedded in a higher dimensional space, say like in this three-dimensional space around us, a lower dimensional object, maybe this one. It's embedded in an ambient higher dimensional space, 3 dimensions, but intrinsically, it's just two-dimensional. It may be bent, it may be, sort of curved, but it's a lower dimensional space intrinsically. It's only exercising two dimensions. Two numbers would tell me where I am on this manifold within this broader state space. And we could argue, and I'm lacking a clear tool that I could use. Perhaps this one is the least bad example. I could take, another tool here, and I could say, well, this is in three space, this cable, but it's intrinsically one-dimensional. And I can quantify that. I could ask, how many points lie within a ball? If I imagine a ball here where my tip of my nose is, and I imagine the radius of the ball rising. It's growing radius around where that tip of my nose has been. And I imagine this radius rising. The number of points included in the object of interest as that ball grows larger and larger rises linearly. It rises with proportional to the radius. By contrast, if I have something which is two-dimensional and I make that ball larger and larger, the number of points included on this object will go up with the square. It'll go, it's pi, pi r squared, right? If I have a three-dimensional structure, my fist or something, and I were to have a little ball rise there, the number of points encompassed goes up with the cube to the r to the cube power, right? And so it is with this notion of dimensionality, the nominal dimension, the ambient space within which the system is evolving, may be far, and typically is far, far, far greater than, in fact, the intrinsic dimensionality, the dimensionality exercised within this. A system that has very high dimensionality may be summarizable, maybe boiled down, if we want to describe it, its location at any one point, to just a few numbers. Here, just two numbers would give me a huge amount of information about how the system is going to evolve. Even if I don't know it's Mary who's infected and Sam who's not, and John who's not, or if it's Sam who's infected, Mary's not, and John's not. Just two numbers, and I could summarize a great deal about how the system's going to evolve over a coming time. So I'm motivating some ideas here, but here's the deal. We've been operating on mimics of systems. We've been operating on ABMs here. I want you now to turn your attention to imagine things in the world. We build these models because they do mimic things in the world, and hopefully it won't be too large a leap to start imagining, real world systems where maybe it's the SIRS system, where you have people in social networks in the world, people in physical systems and there's some sort of spread of contagion, maybe of pathogen, maybe of knowledge, attitudes, beliefs, and innovation, ideas, conspiracy theories, rumors, what have you. Or maybe you're in a predator-prey model, and you're thinking about the evolution of the stocks of predator-prey. An incredibly complex system out there in the world with all sorts of detail about the environment and competing predators and parasites that may separately kill some of the animals, etc. But a system which is coupled with links and hairs intertwined to this day. Here in those systems, one variable, like the number of hairs, is entangled with that of others, like the number of links. In fact, the very fate of a single hair is entangled with, the number of links around where they are, et cetera, right? And here's a key fact, though, and I want you to remember this, and we'll come back to it next time. And critically, we'll be hitting on it in the remaining time here. The information about a hair, the fact that hairs are very, very high, encodes information not only about what hairs were a week ago or what they might be a week from now, but importantly, it does that, but also it encodes information about how links will be, what the evolution of the lynx population is, and what that population of lynx, how it will grow or shrink. If there's tons of hairs around, it's a likely indication the lynx will be growing. The lynx are either very high right now, they're very high right now, it's only very recent. They likely be growing in response to the number of hairs quite quickly to consume those hairs. If there are very few hairs around, it's probably because the lynx population has recently plummeted, has reached a very high level and will soon plummet because there's not going to be enough hairs to sustain them, etc. Let's talk about this a bit algebraically. I suspect those from math background will appreciate this more, but it should be accessible to all. So if we have a predator-prey equation, this is described by the classic Lotka-Volterra equations from early in the last century, which beautifully describe the interactions of two populations. Population of predators, of prey X and predators Y, where the prey grow in the absence of predation, they grow at a certain rate alpha, but prey, that's X, are subject to predation by alpha or by predators. So the product of prey and predators gives a sense of how many meetings of predators and prey there are, and those will lead to outflow. Those will lead to reductions in the number of prey, because predator-prey meetings will lead to prey getting eaten. But meanwhile, with predators, their ability to give birth, to have large litters, to have those new offspring survive, right? The very ability to reproduce in many cases is limited by the ability of the predators to capture prey. And the number of new births that occur is treated as proportional to prey times predators for this reason. We need predators, but we need prey. If we don't have any predators, there'll be no births. That would be Y equals 0. If we don't have prey, but we do have lots of predators, there won't be births either. And then there's a death rate for predators independent of prey. Delta here. Now, what's notable here, if you've never thought about it, is look, take this upper equation, and we're going to separate out Y from the other components. Look, Y only exists at one point here. Y only is found at one term here, right? We could take that term over to the left-hand side, bring this term over, so it's alpha x minus x dot, and divide by the beta x. And here's all the x-related terms, including the rate of change of x, and this is a term for Y. And what this is specifying, if you think about it, is that what this is stating, what is somewhat astonishing. It's somewhat astounding, right? That given information purely about the prey, the current numbers, the rate of change, we can derive uniquely the value for the number of predators that must be around. That's what this is saying. It's saying, given just information about prey, including the rate of change, whether they're going up and down, for example, and how quick, and the number of them currently present, just information about prey. If we observe really well prey, we don't observe predators at all. we could still derive analytically, if we posit this is a good model, the number of predators. Similarly for prey, right? If all we have is information about predators, the Y here, if we know predators really, really well, but we don't have a good way of capturing information about those ghostly hares in the winter whose fur turns beautiful white, we can calculate the number of prey there are at any one time using this information about predators. Now you may say, well, thank you very much. That's interesting, but it's a very simple model. But here's what it's saying. Look, it's saying that when we posit a model structure, here it's a simple compartmental model, but this will hold for our ABMs. It implies the very coupling of predators and prey here, to use as an example, means that information about one part of the system, here, say, prey, gives you tons of information. Here, uniquely determines the number of predators. What's going on in one area of the system that you might think is just one area to measure and you got to measure the predators? No. It's saying, look, there's so much information about that one area of the system. If you have really good information about one area of the system, it tells you everything you need to know about the other area of the system. It pins down what that other area of the system is. And, we can abstract away from this particular example from predator-prey. The same principle is at heart true when we're dealing with complex models that exhibit coupling, right? Like an SIR model or any of these models that we've been examining that have coupling between areas, and that what's going on in one area of the system influences what's going on the other, means that if you have information about one area of the system, it whispers to you, in some cases positively yells to you about what's going on in the other areas of the system. So, I hope this will be carries a certain plausibility from my description, right? If we have a really good observation about, we know the number of infectives is rising very, very rapidly for the number of infectives, even though we're not measuring the number of susceptibles, it's very likely the number of susceptibles is dropping quite quickly because they come from susceptibles. And it's likely that in the next little bit, the number of recovereds will be rising quite quickly because these systems are coupled. What we measure at one place whispers to us about what we measure in another. If we have lots of human cases of West Nile being, coming about, it's whispers to us about high mosquito infectivity rates, right? They're not separate. They're not solitudes. If we know something about high mosquito positivity rates, it's likely that lots of birds have recently died because they have high viremia as a result. So what we know about one part of the system can tell us a world about the other parts. Now, this is a somewhat radical notion because we commonly think, well, look, we need to, if we don't have measurements of this, we don't know what it is. It's a mystery. But what this is saying is, no, what you posit in system structure means if it's a coupled model, which it typically is for coupled systems, it means measurements in one area are going to give you lots of information about what's going on elsewhere. If you just if you just listen carefully in the right way, if you have the right lens to look at it, you learn about what's going on in other areas of the system. You can learn a wealth of information about what's going on elsewhere. And if we look at data from the world, it shows these exact patterns. Here data from UK government on daily reported cases and daily reported deaths. And what you see here should whisper to you very much of that phenomena, right? We plot these out and we see these kind of trajectories being arced out with some, interesting little quirks, but there's tremendous regularities here, tremendous orderliness. What we don't see is just, total, scattershot, sort of splattered down different points here. No, we see some very regular structures, which is positively crying out about the underlying system structure that gives rise to this. That cases and deaths, are not independent, right? That one is coupled to the other. Information about one will tell you about the other. Every bit as much as the heading of a hurricane in a certain direction will tell you about what it's likely to do the next day. We can anticipate evolution of this system by understanding these jointly in these phase-based plots. Daily admission versus new admissions to hospital versus the number of beds that are full. They're coupled, and so if you plot them out, there's these regularities among them. If you looked at each one in isolation, you wouldn't see this, but if you plot them in the right with this lens, you could start to see this. Here we have total confirmed cases and new confirmed cases on the y-axis, and again, regularities. These are not coming by accident. They're not just stochastically all over the map. There's regularities here. They appear in country after country after country. It's not that, Canada is totally different than the UK, totally different from, what we see in Singapore, totally different from what we see in the US. No, there's regularities. Or here, new cases versus change in case rate for this week compared to last. Again, the orderliness screams out at you. It just screams out of the page here. There's these regularities that come out because of system structure. Now, we're not going to have time to cover this now, but I'm going to show you something that's profound. This is proven in the 1980s by mathematician Floris Takens, and it rightfully carries his name, Takens embedding theory. Under a very broad set of conditions, we can reconstruct the structure of the underlying state space of a system. So there's a system out there in the world. We don't know what it is. We don't have a model of it, potentially. It doesn't depend on us having a model of this system. All we have is a single time series about that system. Maybe it's number of phytoplankton over time from the Northern Pacific. Maybe it's, number of infectious cases of whooping cough noted in Georgia for the past 2 years, daily. Maybe it's the number of new cases of diabetes on a monthly basis going back 10 years. Just one time series. We can reconstruct, here's the thing that it says, we can reconstruct the structure of this underlying state space of the system giving rise to it. Again, not of a model. No. This is not positing a model. We're not making a conditional model. It's of the underlying system. We can reconstruct its state space of that system in the world using this time series under a very broad range of situations. And basically, it has to do with coupling of the system. The fact that links and hairs are not solitudes to one another. They interact. And what you see in terms of hair population dynamics, the number and the rate of change tells you all you need to know about the links dynamics and the number of links right now. And so here we are reconstructing not just the thing we measure, but the rest of the system over time. And the way we do it, and I'll be closing with this slide, is through a process, a mechanical process called delay embedding. So we have data over time. That's Y t here. So imagine we have a time series, y of t, time point t. We have a certain value for this one time series. Maybe it's number of infectives for time, right? We have a value for it each day, maybe. That's t. And what we're going to do is for each point in time, except for the very beginning where we don't have this option of having previous ones, we're going to take the value at time t, the value at t minus some delay, maybe it's 1 day delay, the value at t minus 2 times that amount of delay, say 2 days ago, down to t minus n times tau. So maybe 5 days ago. So each time point, except for those at the very beginning, which don't have these previous ones, we're going to have a vector. Maybe it'll be a vector of size 3, the value today, for every day, the value of that day, the value of 1 day before it, and the value of 2 days before it. That's a 3 vector. It's a vector of 3 elements in it for every day. Or maybe we embed it in 5-dimensional space. Maybe we have value now for each time point, and each day we have the value for today, or the value for that day, rather, the value for 1 day before it, 2 days before it, 3 days before it, and 4 days before it. 5 values. Okay. And we do that, and then we populate it in space. We plot these out in space. So if we had those 3 vectors of size 3 vectors, each would occupy a point in this 3-dimensional space. Here's the value at t, and it determines, if we consider what its value is at time t minus 1, that's its value over here, time t minus 2, that's its value here, and it determines this plot. And what we'll see is these induced curves, much like these. We'll see them etched out in this system. And what this is whispering to us about, what it's telling us about, if we have the ear to listen, is the state space or summary state space of the underlying system that is giving rise to this data. And if we have the right way of listening to it, it tells us about things we don't measure directly, but are implied. Just as if we plotted this out for hairs today, yesterday, and 2 days ago, the fact that these curves are going around would be telling us about the number of links on each of those days, not just the number of hairs, that's what we measured, but what it implies is about the links. Now, again, this is not depending on any model structure. It's not depending on we posit this exact structure applies. This is about data from the world whispering to us about the system that gave rise to it, this underlying system, independent of any model, independent if we've ever modeled it. It is coaxing us. It is yearning to share its secrets, not only about what we measure, but things we never measured, but interact with that thing we measured, but which directly or indirectly are affected by or are affecting that thing. We listen for hairs and we hear about links. Okay, that's all we have time for today. We're going to continue on this next time, and we're going to see how this ends up playing out with systems data science and some of the relevance for agent-based modeling. And it's going to give us ways of taking otherwise inscrutable time series that just look random, just look, like they have no rhyme or reason to them, just look like happenstance. And it will give us this lens by which we will see their hidden structure, their hidden orderliness, the system that gives rise to. So that is our goal for next time.